Hello, welcome. Welcome to today's online discussion panel, which is entitled Photonic Integrated Circuits, or PICs, Separating Reality from Potential. My name is Mark Elliott. I am the COO of Europa Science, which is the publisher of Electro-Optics. The purpose of today's online discussion panel is ambitious, I'm not going to lie. We are here to try and explore the transformative potential of PICs, have a look at their current applications, and understand how we bridge the gap between innovation and real-world deployment. I am very pleased to say I have some help with this. Three terrific speakers who I'm going to introduce you to you now. And I would also like to say that there's an awful lot of you watching out there. We've had nearly 250 of you registered to watch. So that says something about the level of interest and causes us no little amount of extra pressure. So I hope you get a lot out of it. Right, in no particular order, I'm going to introduce our panelists today. First of all, we've got Dr. Amir Ghadimi. He is the CEO and co-founder of Lithium AG, which is based in Zurich and is a startup commercializing thin film lithium niobate material platform for PICs. It's got a lot of industry experience, more than 15 years, and that has been in the areas of integrated photonics, silicon photonics, and quantum optics. And Lithium was founded in 2023. So welcome, Amir. Thank you. Very good to have you with us. Next, we have Dr. Ruud Oldenbarven, who is an inductee to this year's Photonics 100, and he is very much a laser physics specialist, with a particular interest in hybrid integration of passive and active PICs, and has been a pioneer in the area of hybrid integration of IMP to SIN to fabricate ultra-narrow line width tunable lasers on chip. So thank you, Ruud, for joining us today, and it's great to have you on board. And last but certainly not least, we have from Legentech, Dr. Anton Stroganov, who is the head of product management and is another of our Photonics 100 honorees. So welcome, Anton. Excuse me, Legentech is based in Lausanne in Switzerland, and his job is to drive the advancement of high-performance silicon nitride integrated photonics by, in his role, bridging the technical innovation with market needs. And obviously, how this stuff is used is going to be really critical, I think. So it's one of the things we want to talk about today. So welcome to you all. Thank you very much for joining us. I think we've got a terrific panel to talk through this. So what are we going to talk about today across the next hour or so? We want to try and understand the current state of play and then cover some insights into PIC innovations and understand where they're triggering breakthroughs and where they are eradicating barriers. So that's going to be about emerging industry applications, of course. I'd like to have a talk about the current challenges. Could that be in the manufacturing end? Is it about the scalability of cost? Or is there somewhere in the R&D process that's creating hidden obstacles? I hope to find out some more about that. Obviously, we want to have an eye to the future. Where are they going next? And hopefully, for all of you watching online, there'll be some useful top tips for the integration side of things. That's a really important point. These online panel discussions are designed to be useful and interactive. So we would welcome any questions from you as we go. You should see at the bottom of your screen a way to submit questions, and we'll do our very best to tackle them across what I hope will be a very full and lively discussion. Okay, so to get that discussion going, I am going to kick off with a general question, and I'm going to start with Amir because he's top left on the screen as it's facing me, and then we'll work our way around. So I'm going to start with a general question about PIC technology and to understand whether you think it is reaching its potential. And that could be about its energy efficiency, of course, which is obviously a very big topic, miniaturization and general performance. What's working? How is it doing as a sort of technology, would you say?
No, thank you so much. First of all, thanks so much for having me and having us and organizing this panel. So with regard to PICs, I mean, look. I remember that actually since my started my PhDs in 2011, 2012, it was promised that actually silicon photonics is going to be commercialized 2 years from now, and that pushed 2015, then 2020, now 25. But I think ultimately integrated photonics is having its, let's say, moment in the sky. And obviously, when we are talking about, so photonics, when we're talking about photonics as a whole industry, it's much bigger than integrated photonics. I mean, photonic is bigger than, it's all around us. If you look at your, like, let's say, typical cell phone, I mean, it's pretty much a photonic device. I mean, it's used as a consumer electronic, but the display, that's a photonic device. Your, let's say, face projector is a photonic, the camera is a photonic device. But traditionally, when we are talking about photonic, I think one of the main domains has been always telecom and datacom, right? Sending data. And I think that's been a traditional domain of telecom and datacom. And the thing is that over the years, PICs were kind of competing against much simpler technology. Like if you look at what traditionally people make the transceivers, they just literally go into Asia and glue single lasers, like VCSELs or EMLs. And up to around the 400G, like sticking in 4 lasers to 4 fibers was much simpler and cheaper than actually have 2 lasers and a PIC and a fiber. But as we are going to like higher and higher data rates, like when we are reaching like 800G, okay, still like 8 lasers, but definitely when going to 1.6 terabit, which is actually, I think that's, in my opinion, is a really true moment of photonic integrated circuit to shine. They really start to the mass make sense from the not just a technical perspective, but also commercial perspective. Because like transceiver manufacturers are now dealing with this dilemma. Shall they just stick 16 lasers or having 2 lasers and 1 PIC and 1 fiber? Just constructing this is a different game. And I think it starts to become commercially makes sense. Right? PIC has been really driven by a lot of engineers, but they were going against technologies that are often far simpler. And finally, I think we have a sort of moment of break. I think Anthony Hochstein in ECOC had a very nice talk to say we are approaching golden age of optics, especially going toward this like high data rates. And I'm very obviously optimistic that we made a company in this topic. So, but I hope that in 5 years, I will not come and say, okay, silicon photonics, or let's say integrated photonics is another 5 years ahead. But I think finally we are there.
Okay, that's a very interesting lead. I'm going to go obviously to you, Anton, next. And so golden age of photonics. I mean, are we there, and are PICs driving that, do you think?
Well, here probably we need to open on a positive note. And of course, I agree with Amir that communications was always driven by optics, and it will continue this way. But probably I will start with a bit more generic point of view, and probably with a positive one, because generally nowadays, pretty much any optical component can be integrated on a chip in a quite robust and scalable manner. And this is really nice because you can have very compact, very broadband components. You really can eliminate quite a lot of unnecessary interfaces and complexity, and this really drives your efficiency forward. And besides that, of course, you can also have the efficiency gains from the device configuration itself. For example, when we compare bulk lithium niobate with thin film lithium niobates, pretty sure Amir can comment on it more. But of course, there is this optimistic point of view. But if we are a bit more critical and realistic, I believe in such kind of discussions, it's always very important to really define the system about which you're trying to kind of discuss certain points, and specifically define what is your actual efficiency or performance metrics, right? Because otherwise it's very difficult to compare things. And therefore, if we speak about purely the optical part, I believe, yes, you can really realize very great devices with reduced size, with reduced power consumption, with reduced weight, but still, there are still these interfaces with the outside world, with the fibers, with your readout systems, with your driving electronics. And I believe it's just that in the recent years, we've really seen the movement of the engineering challenges or bottlenecks from optical parts to somewhere else. And I'm not saying that it's bad or we cannot resolve it. It's just to mention or to point out that when we discuss photonic integrated circuits, it's always really just one part of the equation, and we need to see the system as a whole to be able to make any conclusions or statements.
Ruud, thoughts on that?
Yes. Well, I tend to agree for a large part with what the previous two speakers have mentioned. So I've been around in this field for quite a long time. And what I saw, especially when I started, was we had to fight for every customer. We had to chase everybody continuously, and it was difficult. even though at that time there was already a large time has passed over research, and everybody said, yeah, it's going to be the next big thing. But integrated photonics has been the next big thing for a very long time. And when I started, like I said, we had to chase everybody. And then for me, I think the tipping point was around 2015, maybe 16. There seemed to be interest from first the larger organizations doing exploratory research into integrated photonics, figuring out that there is a lot more to do than just single component devices. Having said that, there's still a large interest in single component devices because pluggables, basically, they are easy to replace. So if you have a very complex system on your chip, you can add a lot of functionality, but that also means if something breaks, you need to exchange a lot more. So that's the downside of it. Then what I also see is there's the promise of low energy per bit, and that's also what everybody wants, right? But in integrated photonics, we have this one really stupid thing. It's called a heater. And at this moment, most people are using heaters, and it's just wasting energy. And it's so the moment there's an actual commercial option for going to something else than a heater, that will be great.
Do you see that coming? Is it years away? Is somebody working on this now? You know.
Oh yeah, of course. There's everybody agrees that heaters are unwanted, and yes, there are a few other options. So you have, if you want to go for really high speed, you have either the electro-optic method, so PN junctions or whatever, or you go for stress optics.
Yeah,
stress optics has been difficult, and the amount of stress induced versus phase shift, it's very low, so the devices are very large, so it goes at the expense of footprint. But yeah, so there are some options. There are a lot of options being explored on different platforms. So yeah, we'll see what the future holds. I'm very excited to see what happens.
Yeah. I mean, Anton, any thoughts of when you think we're going to see this sort of breakthrough? Are we talking a couple of years, or is it further ahead than that?
In my opinion, I think what what has been said by Rudy is completely correct. And definitely, like the thermal optics have been a hack solution, but now they need to be replaced with something more permanent. Of course, like we are in a school of thought that we believe like electro-optic materials are the solutions. Therefore, we made a company around this concept. And I think we are already there. Like a lot of people have demonstrated this. I mean, like when we go and then talk to customers, nobody questions anymore if this works, especially like TFT technology. All the questions are, can you now supply it in large volumes? And I think this is still a challenge. Of course, silicon photonic is ahead of any other else because they can easily pigtail on CMOS industry. But the problem is that silicon is not the best photonic material. Right, it's a very good electronic material, but when it comes to photonic, it has a lot of shortcomings, such as relatively high losses, really low power handlings, low transparency window, not intrinsic electro-optic effect. Actually, often I always say that the most interesting fact about silicon photonic is not the silicon itself, it's germanium detectors that can be easily integrated. But when we are coming to alternative materials, TFLN, BTU and other things, I think is like scalability is by far the hugest challenge.
Okay, I'm going to ask about challenges in a second, but Anton, this is your opportunity to defend silicon as a photonic material, or not?
We are working with silicon nitride, so I would not defend silicon. I would defend rather our platform. Yeah. It's a bit selfish, but we are believing in it. So generally, I believe what was mentioned is fully correct because everybody wants to have fast modulation. But previously, or if you take an approach when you just use a single material platform, then typically it's been at the cost of something else, typically at cost of propagation loss or some other things. And I believe that's why within the recent years, we've seen quite a consolidation of opinions within the community that heterogeneous integration, so basically when you combine different materials on a single platform, if you wish, or just do a appropriate scalable integration of different parts to be able to enhance the functionality, is really the way forward for a broad range of applications, I would say. And this is where we are at least very active. And we already providing this electro-optic material on silicon nitride, so the issue is partially resolved. But as Amir mentioned, the key challenge that community sees now is really about having the robust supply chains for that. Because one thing is when you can demonstrate, the next thing when you can really have an industrial prototype, but then there is quite a huge step to make it scalable and robust enough to serve large-scale industries.
Yeah. It's a definite truth or truism that on all of these discussions that I do, at some point we quickly move on to the challenges rather than the opportunities, because I think in a lot of cases these technologies are struggling with the scalability for sure. So that's obviously a challenge, right? And I'll start with you, Ruud. I mean, is that the main challenge, or are there other challenges we need to think about in terms of how PICs are being adopted and scaled?
So for what I can see and what I can tell, there's a few big foundries. So IMEC is doing quite a few thousand wafers per year on 200 and 300 millimeter in silicon on insulator, silicon nitride, combination of the two. So we also have the platform where we combine both the low loss silicon nitride for power handling and easy coupling, and PN junctions and photodiodes on the silicon. So scalability for some of these platforms are already there. But indeed, the moment you want to add a light source, then you're done. There's no proper option yet. So there's a few options like what they call edge coupling or butt coupling. You have flip chipping, you have micro transfer printing, you have wafer scale bonding. That's the one with the highest volume throughput. So then we're talking about companies like Tower and Intel that do this type of approach. So they have the higher volumes already under control, but it goes at the expense of yield, right? So that is, I think, the hybrid approach. So adding the light source, that's going to be the most challenging part for the scalability, on top of packaging. Because then you have your wafer and then it needs to be packaged somehow to connect to the outside world. And at this moment in time, packaging costs 80% of the entire cost of a photonic chip. So that's the second challenge that needs to be addressed, is getting the packaging lower in price compared to the price of the photonic chip itself. And ideally, we would go down to the same path as what electronics is doing, EIC, where the packaging is 20% and the EIC is 80% of the price.
Okay, that's interesting. I want to talk about other challenges as well. And one of the things that you were talking to us about, Ruud, when we were talking to you late last year, was about the talent pool, the engineers that we need who have specialisms in this area. And it tallies a little bit with a question that's just come in from somebody in the audience about specific degrees and masters which would be aligned with these kind of areas of kind of technology development, I guess. I mean, is talent and the availability of the right people to get this technology scaled and developed an issue? And what are the solutions? Could this suggestion from one of our audience be part of the answer? Are we training enough people? Are there enough people in the workforce? I'll go back to you, Ruud, and then I'll open it up more generally.
Yeah, please.
Okay, so yeah, what do you think? Yes, is there a big problem with it?
Yeah. So what I observe, it's twofold. On one hand, it's still very much a highly educated field. So most people have at least a master's degree. Many people still also have a PhD degree. And in my opinion, if we want to have the integrated photonics accepted by the rest of the world, it has to become more generic, which means people with a non-PhD background or non-master's degree background, they need to be doing all of the manufacturing and all of the getting this stuff out in the world, because there's simply not enough PhDs to go around. And I think that will also help in lowering, lowering cost, because at a certain moment, having many PhDs also just is too expensive, right?
Yeah.
So that's I do see that there is a need for it, but this is also one of those chicken egg problems. Is the market ready for high volume PIC? I'm not sure. So there are a few markets which seem to be ready or getting ready, but we're not there yet.
Okay. Anton, I saw you nodding a lot during all of that, so I'm going to go to you next on this issue. So talent as a problem or other challenges to talk about that are facing the sector?
Well, there are always quite a lot of challenges, but if we stay on the talent pool, I would agree that there is quite a clear need to educate more people, and it's not only about the workforce. I really believe that to be able to achieve the market adoption, you need to raise awareness. And you always start from the people who are studying something which is close to this domain. So probably you do not educate just PhDs or masters in photonics. You really spread the program or knowledge to people studying the applied physics or something similar. So you basically do it stepwise, but it definitely helps with the adoption of the technology and with understanding of the potential of the things that you can do. Because when people cannot even imagine what they can do with the technology, it's very hard for a technology to progress because you just don't have any early adopters, right?
Completely agree with that. I think it's an issue we hear a lot, not just around this particular technology strand, but just photonics as a concept in general. It doesn't have a lot of resonance beyond people actually working in the discipline. So, Amir, you agree with that, or any other challenges you wanted to highlight at this point?
Sort of, kind of, as a, let's say, sort of a person of an earlier stage startup, looking at this. I mean. Like I was talking to one of the investors just this morning, and they were asking us what are the challenges. Exactly the same question. For me, by far, by a huge margin, is not manufacturing nor testing, none of this, not even funding, not even customers, is hiring. Like it's been by a huge margin our biggest challenge. I mean, we have sort of, if you go to our website right now, we have like 8 or 9 open positions. We still are struggling to find the competent people with the right mindset to actually fill them. And I mean, personally, like I would have never imagined before doing it, but 50% of my time is around, sort of hiring. So yes, I would say that this is probably, one of the, at least for early stage startups, is one of the biggest challenge to find people. And it's kind of Photonic is really booming. As I started with this opportunity of golden age of AI, golden age of optics and data center hardware. The challenge is that there's a lot of also people are jumping to this big opportunity, and they're all, let's say, fishing for the same talents. So I think we are a little bit in the photonic in the area that actually there are more positions than there are people in it. And I agree with Anton and Ru completely that still photonic is in its infancy stage. So it's mostly run by PhDs or people having master. It's not yet a skill that you can run it with technician level stuff. So but I mean, and there's so much of like the PhDs and masters are graduated every year, and there's like a billion different companies are hiring. This, in my opinion, for at least an early stage startup, is by far the biggest challenge that we have right now.
Okay. thinking about what's going on then, so parking the challenges, parking what might be further down the road, where are we seeing specific industry-specific use cases which are standing out to you as experts in the field, as great examples of what can be done? Amir, I'll go back to you if I may.
Yeah. I mean, there are things that actually are coming in the future, and then there are things that are now. I mean, and what I'm about to tell might actually looks a little bit controversial, but in my opinion, there is only one industry that actually using the photonic in a real sense, and that's just telecom and datacom. That's it. Anything else is just purely research, right? It's like low volume research level. There are a lot of opportunities in future, like I can name, quantum. I'm particularly interested in also space-com, as well as other sensing, all sort of complicated sensing and sort of application people are pushing. But in my opinion, the people who are today are really or have the money or need to write $100 million check is just hyperscalers and transceiver company. That's it. Anything else is government funded mostly, or is it in the future? And that is a reality that it's been, again, like one of the challenges with photonic is being that it's been mostly pushed by one industry, and it's going to remain, in my opinion, within the next 5 years. I don't see any other company, like any other industry, who is jumping in, not just because it's cool, but they are willing to write a big check to get the thing done. So I'm again happy to be be proven wrong, but realistically, I think telecom and datacom will remain by a huge margin the biggest application.
Okay. And so it could be a controversial position there. I don't know whether anybody wants to sort of contradict or give a, is he right? Is it only telecom and everything else is sort of somewhere in the near to far future? Anton, what do you think?
Well, I would tend to agree that communications market is definitely the one driving it at this stage, but I would rather disagree that it's the only application domain. Because first of all, we need to make it clear that there are markets which require a huge amount of chips, but typically it also comes with a low margin, high competition, low price points, and so on. But also there is quite a large variety of markets which do not demand really millions of chips. Maybe they can live with thousands or even hundreds of chips. But these are real applications which are being applied quite widely in our daily lives. And from our standpoint, we can say that there are quite a lot of different domains which really have products based on integrated photonics nowadays. And of course, there is this future markets, quantum, first of all, which have now quite a huge R&D spending and so on. Of course, it will come because, at least from my perspective, there is a very clear value add from integrated photonics to the quantum computing, quantum sensing, and something else. But from the personal standpoint, I'm quite a strong believer that everything which is related to sensing, for example, so here it can be biosensing, chemical sensing, spectroscopy, LiDAR, so sensing in a quite broad sense. These are the markets which are already quite active and which really use integrated photonics to be able to be more efficient, both in terms of the performance, technological performance, and the commercial offering.
And are there, you don't have to necessarily name them, but are you aware of any specific applications that are actually being used, even on a relatively small scale in those sectors? Would you say that there's evidence?
That's for sure. I just would like to stay intentionally a bit generic, because you can imagine we are bound by NDAs and so on, so we can refer to the public information only, but you can always see all the, basically, even from the publications or some other domains, you can see that spectroscopy really benefits, or LiDARs benefit from the narrow linewidth lasers. Yes. Of course, there are some limitations about the tuning without the mode hopes and so on, but there are some particular domains. I would not call them niche, even though they are small volume, but I would not call them niche, which really use these devices straight away in their products.
Okay. So Christine, who's messaged in about this, there's your answer. Yes, but we're not telling you necessarily where exactly. But watch this space and research. Rude, anything to add to any of that?
Yeah, so what I... Again, it's pretty much said already, most of it. So what I see, indeed, it's the sensing LiDARs is promising to be a large field. Has been promising again for a long time. And the first couple of startups from 10 years ago have gone bankrupt, and now there's a second wave. Everybody doing LiDAR tends to agree that integrated photonics seems to be the next solution. And it's getting closer and closer. So the market adoption, expected market adoption from tier ones, tier twos, even the automotive manufacturing, it doesn't really shift all that much. So 28, 29-ish, they expect that LiDAR modules will be deployed into automotive. And then whether it's old-fashioned LiDAR, so to say, like a pulsed LiDAR, or if it's integrated on a chip and FMCW, that's to be seen. But 28, 29 seems to be the general consensus, which is, of course, a huge market, automotive. Next to that, indeed, datacom, telecom, those are the huge markets which are driving this field for I don't know how long, and also for us, it's the biggest customer base by a long shot. On the other hand, what I see and what I personally find very interesting is you have on one hand these options for extremely large volumes, low margin options. So that's LiDAR, which needs to be low margin. You have the telecom, low margin. Or you have the very high margin, very low volumes. And then I'm talking, for example, satellite communications. You don't want to shoot something into space and then after a few hours, it doesn't work anymore. So it needs to work. And then it's fine if it's a bit more expensive. If it's hugely expensive, it's still fine because the entire satellite is expensive. And what I find very interesting is there's not that much in between. So there's maybe a few markets which are sniffing around, but there's not much in between the high volume, low margin and the low volume, high margin. And I think for gas sensing, Anton already mentioned it, that would be the medium volume market, at least at this point in time. And then in terms of application, you can think of agri-food type applications, where you can, for example, sense the fruit readiness, like how ripe is your apple, or on the agri side, measure all these gases from cows or other animals, which is in at this point in time, especially in Europe, it's a big thing that all these exhausts from cattle are in need of monitoring.
Yeah, that's a terrific summary from everybody on the sort of state of the nation, I suppose, or state of the nation in terms of where this market is at. So I want to move now towards perhaps something that could be defined as a bit of a useful takeaway, and ask about, from your experience, about the deployment journey. So where these journeys are involving PICs, I'd like to ask, what differences should end-user application developers and engineers be aware of when considering the different kind of PIC technologies which are out there? I mean, I'm thinking obviously of things like silicon on insulator or quantum PICs. So what sort of things do these engineers and developers need to be thinking about depending on the different kind of technologies that they could choose from? Anton, I'll go back to you, if I may, on that one first, just to kick off.
Yeah, so here, I believe if we really try to simplify it to the extreme, there are only probably three main questions that you need to ask yourself and your potential suppliers. First is, when you're assessing different platforms, can you do what you need with your platform? Second is, can you do it at a required scale, what we just discussed before? And the second, at the required cost. So basically, the first one will allow you to assess technical feasibility. Can you do your functionalities that you want? Can you integrate the lasers or photodiodes? Can you modulate at the required speed? Or can you even just integrate it with other parts of your system if there are any other components around it? The second part about the scale, well, what we just discussed, do you need tens of chips? Do you need thousands of chips? Do you need millions? And whether the industry or the platform to which you want to go is mature enough to be able to supply it to you. Because nowadays we see quite a lot of new players, we can see quite a lot of new technologies which promise a good performance, but actually they are not ready to supply at high volume. And this should be really considered from the very beginning, especially if you target these large volume applications. And the last part is basically cost, because generally there are always two contributors. First, it's about the cost of the material and manufacturing itself. And here, of course, indium phosphate, silicium niobate, silicon nitride, silicon, they will have very different benchmarks. And you need to understand whether it's within the commercially viable window for your product. And the second part here is always, at least how I see it, it's about the maturity of the particular platform or particular supplier, because this is basically what will ultimately define the yield of your particular circuit. And it could be quite a big contributor, especially if the platform is not very mature, because maybe some of the produced chips will just not match your requirements, and effectively it's an overhead for you. So again, don't really focus on the one-to-one comparison, let's say, of the platform. For me, it's always you start with these very basic questions, you sort them out, and from the experience, as soon as you have these answers, you typically have quite a clear understanding of what you actually need.
Okay, that's really good advice. Ruud, from your experience, are people coming in with these questions clear in their heads or not? Is it very exploratory at the beginning?
Differs from customer to customer. What I see sometimes it's people that really have no idea what they want. So you need to guide them a lot, and some people really know already what they want from the beginning. So it's for them really just give me this particular device with this particular performance, and then it's done. But coming back to your original question, I think what people just exploring this field need to take into account, first of all, is the long turnaround time. So we are unfortunately not at the speed of EIC electronic fabrication, which is 3 months. And if you're 3 months and 1 week, then you're out of business. Typically, for PIC development, we're talking easily half a year of fabrication time, because the market is not big enough to speed up yet. So that's one thing to take into account. Iterations take a long time. The second thing that I would like to stress for people that are just starting here is design not necessarily for your PIC performance, but for your system performance. So you want to look what does your system require, and then calculate back or trace your steps back. What do you want as a PIC? And that sometimes means that you can do with lower performance if your system therefore has a higher performance.
Okay, that's useful. I mean, I guess it's, as you say, some of the challenges to do with the relative scalability of what's already out there that allows speed and cost to be kind of better optimized. I mean, from your perspective, would you agree with that, or anything else that you think we haven't talked about on that?
No, I think that this is very well said, by both of the previous speakers. Definitely, cost and performance and maturity is really important. The thing that I want to actually sort of maybe add on top of it is that photonic field as a whole still is a high-end product. Right? We are not yet at the commodity level, which means still most of these developments is still performance-driven, right? So, I mean, the bulk of the people, even the people who are looking for cost, they still are trading performance for cost, right? Either higher speed or lower power consumption. So it still is not a, let's say, commodity industry at the moment, which is a curse and a blessing at the same time, right? And here is that, honestly, like, another aspect about photonic that makes it complex is that unlike electronic, we don't have one hero material that can do 99% of the things that people want, right? So, there are different platforms, there are different capabilities, right? Like you have platforms which are suited for making, like, generating and detecting light. There are platforms that are suited for, very like passive optics at low loss. There are platforms suited for like high speed operations. And unfortunately, often not all of these are coming to one. So choosing the platform itself is often, let's say, one of the biggest, sort of decisions that, often as a system integrator or system developer, you have to take. And if you sort of don't do it carefully, it would be a cardinal sin, right? It would be incredibly difficult to recover from it if you go down the path and then do, few tape outs and say, oh, well, oops, this platform has this issue, right? So in that sense, is still, I think it is kind of part of all of our job is to educate the industry about the capabilities. I mean, often we have a lot of customers have good idea, but they just don't know what tools are available in different platforms. And I think as a whole community, especially like, sort of both sort of IMEC and Lighting are doing an excellent job, but I think as a whole community, we have to educate. One of the, I think, important successes of electronic industry was that they had amazing models, right? So if you're a photonic, let's say electronic designer, like a VLSI designer, you don't need to know almost anything about the device. And if you're a device, you don't need to know anything about the fab. So like they're really hierarchical thingy that every layer, provides proper models to the next layer that you can abstract it. We don't have that maturity in integrated photonic yet. So definitely the designers, even if they're doing layouting, they still need to be physicists and understand what is the physics of design. And I think this is an area that needs to be, massively improved. Of course, it took, electronic industry, 40 years to get there. So we're sort of 40 years behind. But I think nonetheless, we have to do that level of abstractness from one layer to the other layer.
Yeah. Okay, no, that's a very good point. And actually, it's a very good segue into what I was going to ask you about next, really, which was about your specific experience around thin film lithium niobate platforms. You made that point that the platform choice is really important. So where is that being used? Which applications are you helping to create, with that platform in particular?
Absolutely. I mean, of course, lithium niobate is, contrary to what, a lot of people might believe, is not a new photonic material. It's actually probably one of the oldest photonic materials that's been, around since the 70s. It's actually not, we are not never saying that we are inventing a new material. We're kind of reinventing one of the very old and mature materials in form of thin films. So you can actually use, semiconductor CMOS tools to process it. But the lithium niobate has been always very interesting for the whole community because it has this magical property. I mean, okay, 8 years working with this material, still it blows my mind that you have this magical property to apply electric fields, and if refractive enough, the materials changes. And this magical property allows you to electronically control light on a chip. Right? And it's very important because if you cannot control light on chip, the thing that we can make is boring, passive optic, which is nothing but matrix inverter, right? Things become interesting when you can actually control light. Like we just don't want the light just to propagate, right? And lithium niobate have that intrinsically on it. And what is really, beside the, let's say, scientific curiosity is that now there is a real demand for it because obviously, I wanted to actually start by saying that there is a huge opportunity in front of us, this data consumption. So as a species, we are exponentially consuming data. So a lot of hypes come and go, .com bubble, social media, but our data has been continuously growing 100x per decade. And and most of this data in a long distance, including this very conversation we have, is being carried over optical fibers. now is becoming closer and closer to the data center, to the rack at the chip level. And as they are getting closer, the numbers are going higher and higher, right? So we are going from hundreds of thousands to millions to tens of millions. This is what I mean by the really golden age of optics, because finally we are in a regime that we can think about tens of millions that was like unreasonable, like unthinkable before, right? So TFLN, obviously, sort of what we are trying to like serve is this trend, right? So we always sort of saying that, lithium is not about TFLN, it's not even about PIC, we are about data. Like we are the guy, your guys, if you want to call that you need to move mountains of data very efficiently and very fast, it's a very suited platform, right? But we are also very self-aware, like any other technology, it has its own limits, right? We don't have any technology that will work indefinitely. For the moment, especially for the markets of 1.6 terabit per second, 3.2 and above, TFLN seems to be very suited because it promises typically what silicon can do at twice the higher speed at 4 times lower power consumption, right? So, and this is a really important factor. We always, always have a saying is that, sort of, when you go to data center operator, they often have two costs. One is the cost of material, bill of material, BOM. The other one is the cost of operation. Bill of material is your chips, GPUs, your cables. The cost of operation is your electricity, CO2 bill, maintenance, other things. The value that actually, our chips are providing for our customers, especially in saving of cost of operation, is so high that often if our competitors give their chips for free, still is more expensive.
Okay, that's interesting. And in terms of your perspectives, Ruud and Anton, on this, I mean, this sort of sense of kind of progress that's being made in this space at the moment. I mean, where do you feel in your kind of working lives this is most evident? I mean, I'm going to go to you, Ruud, around your line width tunable lasers on chip. Where is the demand sitting for that at the moment, and what sort of innovation do you think it represents in a similar way?
Well, the thing is, any integrated optic device needs a light source, right? Otherwise, it's completely useless. And that's sort of what we're trying to tackle, is providing the right light source. And when I started doing this, I think it was almost 20 years ago, we first looked into tunable lasers because that seemed interesting for telecom applications and maybe some sensing stuff. Then, as it turns out, when you combine indium phosphide and silicon nitride, especially low loss silicon nitride, then you get extremely narrow line widths. At the time, it looked very interesting, but it's been 20 years and still there's no need for extremely narrow line width lasers. But it does give you the opportunity to play around with the specifications. So if you have some on-chip filtering that you then feed back into your indium phosphide gain or whatever other material there is, you get the option to play around with different optical parameters to make a laser specified to the needs that you have. If I, for example, look at LiDAR, you want to have higher power, you want to have reasonable low line width, but nobody needs 1 kilohertz line width for LiDAR. 10 kilohertz or even 100 kilohertz is sufficient, but you need the high power, and you need sometimes you need the tunability or chirpability. So everything has its drawbacks and potential options. And I think that designing it properly on a PIC has a lot of benefits, and that's typically what we're now looking into, is making sure that the light source is no longer the bottleneck. So, for example, if you take an off-the-shelf laser, you will design the rest of your system around this one particular off-the-shelf laser. So that means that the laser is the bottleneck. And in my view, the laser should not be the bottleneck, because we have more than enough room to play around with the different parameters to make sure that the laser is the right source that you need, and you can optimize the rest of your system without worrying about the laser.
That's brilliant. And what I love about doing these is you get these brilliant sound bites. The laser should not be the bottleneck. That's one I will take away with me, along with the golden age of optics, which I also particularly like. Okay, so Anton, I'm really conscious of time, so we've got some questions we've got to get to. I'm going to ask you about your kind of working life, if you like, and your kind of focus on silicon nitride PICs, and what sort of considerations that should be taken into account when deciding what kind of modules are needed for particular applications. How is that playing out in your day-to-day life?
Yeah, it's a good question. So maybe I will take one step back, especially for those who are a bit less into the ecosystem. So what do we mean by a module itself in the manufacturing? So at Legentech, we really advocate this modular approach, what we call a modular approach, which means that we start with just something very basic, with basic waveguides, and then we have a set of add-on modules on top, which are practically just a set of additional processing steps, so you can really enhance the functionality of your circuitry if you wish. It can be, for example, I don't know, partial edge of the waveguides for polarization management, for advanced gratings, or something else. Could be cladding removals for integration with other materials, for sensing applications. It can be multi-layer photonic structures. It can be electro-optic modulators, what we've just discussed. And what is nice about the modular approach, it's more or less like a Lego. So you can really choose exactly what you need. They are cross-compatible generally, which means that you can really have a very appropriate combination of those on a single chip, which meet your particular demands. And why it's nice? Because the opposite of it would be just to have a single process which you run every time, which has everything, and it doesn't matter whether the user needs it or does not need it, right? But if you have a modular approach, it really gives you a flexibility, and it's both about the convenience for a user and about the cost efficiency, because you can really reduce the unnecessary complexity. And if I come back to your question, so how do you approach the choice of these modules? So I guess here, again, I'm quite a big fan of simplifying things to the extreme, because quite often it resolves a lot of questions. You start with something very simple. So what is my wavelength? What is my polarization? Do I need waveguides which are high confinement because I do nonlinear, or low confinement because I do sensing? And already with these extremely simple questions, you can define which waveguides you need, right? And then it's just about these additional modules. And there I would not even be worrying as a user, because at least speaking about from our perspective, we have a lot of experience with a variety of projects and a variety of domains, and therefore for a platform there is a very high, how should I say, user-friendly guidance on which modules are needed for each particular functionality or each particular application. So generally you have just a more or less design manual. You say, I want to have a sensing, and then there is module for sensing A, B, C, and you can choose according to what you need. And in this sense, really, you can either go on a menu-like choice, or you can explore whatever you want, because you still can choose from all of the sets, and you can really explore your inventive steps, let's put it this way.
Yeah. So the takeaways I'm hearing from this are very much keep the questions simple, because there's a fairly well understood pathway to get you to where you need to go. Obviously, talk to the people we see here on what you need and why you need it, and you will probably end up with something very quickly that kind of aligns with the use case. We are nearly out of time, so I'm going to jump to a couple of questions which have come in over the last few minutes around some of what people have heard. And we've had a question here about novel material platforms, I should say, such as AIN, GAN. Any thoughts on whether they will be available commercially soon, and any thoughts on those platform materials or material platforms, I should say, sorry, in isolation? Good, bad, useful for X or Y? What thoughts? But perhaps start with commercial availability. Anyone? Amir, you go first.
Again, coming back to that, the statement that I made earlier, we don't have one hero material, in photonic. That's been a blessing and a curse. The blessing has been that, unlike sort of silicon electronic, which is like now two foundries that are dominating this, there is a lot of actual innovation going on in photonic. The curse is, being like, again, I want to take a little bit of a controversial statement here. Is that they're technologically interesting, commercially not so much. And I would compare it with something like the mother of all of these platforms, which is silicon photonic, right? And I would say the curse of silicon photonic, again, it's a difference that actually is a cool thing that as an engineer you like it, and the realities of the market. And unfortunately, with a platform like silicon photonic has been just good enough. It was never 10 times better. It was just 10% better, right? So, and the problem is that, like, sort of when you have a simple solution, just gluing lasers to the fiber, all of this complicated technology you do in PIC would become, meaningless in a commercial standpoint. So lots of this, stuff, and we are following them. They are technologically interesting. They offer, like a little niche here and there, but none of them offer something which is massively, sort of different, like 10x, right? Can do 10x lower power consumption or 10x the speed. And if that, let's say, massive step is not there, it still will be a domain of engineers and research. Right? And again, my job is to say, like, they are probably commercially is not relevant, and it's, I think, our audience job is to prove me wrong ultimately, right? Okay. So people are going to try it and then prove it was wrong, but realistic, and I'm saying it with a tear in the eye because I love to see this, then let's say technological marvel be materialized. Realistically, if I look at the history of silicon photonic, if you're just 10% better good enough, it's not going to cut it.
Okay, so we're looking for a quantum leap forward, if you like. Ruud, Anton, any thoughts? Is he wrong, or or do you think one of these could offer that?
So what I think is there is indeed a lot of different platforms, right? And that's due to many people thinking, I want to have something different and it doesn't exist yet, so let's try this. A lot of platforms are already commercially available, also for high volume, and then high volume, it's mostly the silicon nitride and the silicon on insulator, which are available in large enough volumes for pretty much whatever you have in mind. There are some upcoming platforms which either have a wider range of wavelengths that are available, like aluminum oxide, or higher speeds like lithium niobate, or really low loss like the Ligantech work. But other than that, I believe, mostly it's still niche markets for most of the platforms also.
Okay. And Anton, you agree with that?
I fully agree. It's very hard to add after these two replies. So if I would be a researcher and it would be just the next topic to research for several years, I'm all in, because nice materials, many things to explore. But if we assess it from the commercial company standpoint, well, companies need to have a business case behind, right? And for these materials, as Amir mentioned, it's rather an incremental improvement that you can have, and also to go from the first demonstrators to the commercially relevant offering, as we've discussed at the very beginning, it takes years and quite a severe budget. So these are just decisions to be made, and unless you have a solid business case in the industry, I would say it's very hard to predict when and whether these new materials will be really commercialized.
Okay. So I think, for anybody watching, I hope we can get everybody back in maybe a couple of years' time and see whether any of that was right or wrong. I'm going to end on the final question I'd like to pick up on, just this it's slightly controversial one, which was from Krishna about this heterogeneous integration progress, and the comment is, standalone application with PIC is not a cost-effective to pick the sensor market, and as well, support lags a long way behind technically. Is that right? That position, is that fair, or are we in agreement with that? That's question 4 that's come in. What's your take on that? And if anybody wants to take that question for us, it's basically saying it's not cost effective, and the support just isn't really there to be able to sort of support the technology.
I can say something. I mean, certainly, it has truth in it. I mean, it's always I have a mixed opinion about this. Certainly, heterogeneous integration. I mean, I think everybody agrees in this panel. At least, I think I wish I could be more than 100% sort of agree with Anton that it's a future. And this is probably one of the biggest weaknesses, because monolithic, we are pretty mature in silicon photonic, right? So silicon photonic can actually pigtail and CMOS industries mature. The moment you start doing surgery, that is going to be your limit, right? It's like you can actually drive it, it's like an autobahn, but if you go to a steady, so that is going to be your limit. And right now, this is the limit of indicative photonic. You can do 1,000 wafers and see what, if you want to do a surgery, and it's not yet mature at all. A lot of people are working around it. In my opinion, it still years to become something commercially available. However, on the other hand, I would argue that it doesn't mean that actually PICs are necessarily, without having this, or useless. If you look, there is an actual demand, and this is what I'm trying to say, is not an engineered push, it's a market pull. If you look, for years, for decades, you go to transceiver, you go to OEMs, they glue single laser at a time. And they could live with it, and they are producing 1 million. So if there is a large demand, if somebody who's willing to write a big check, these technical challenges can be overcome. Yeah. Right?
So we're waiting for this kind of market commercial breakthrough, which pushes the technology forward in a defined direction. I think there's clear momentum across a range of areas, but we're looking for that big breakthrough point. I am afraid we are out of time. We've taken up enough of these very busy men's afternoons already. So I just wanted to, first of all, thank them again for their time today. Thank everybody that's watching. This online discussion panel will be available on electrooptics.com for the foreseeable future. So if you wanted to refer anybody to watch this as an on-demand webcast, if you like, you please pass them in our direction. Please tell everybody that you found it useful. I think I've come away with some real insight and some very, very good sound bites. I'm very pleased and grateful for our speakers' contribution to that. So thank you to our 3 presenters today. They have been great. Thank you to everybody behind the scenes here at Europa Science has made it happen. And thank you also to everybody watching this from home, office, wherever you're watching it. We have many of these online discussion panels with many of our Photonics 100. So thank you again. We've got another one on the 26th of March about laser applications in biotechnology and medicine. But really, that's it for today. This will appear as an online article in a few weeks, so keep an eye out for it. Please pass the word on. Thank you again to our terrific speakers today. You have been brilliant. Thank you.
Thanks so much.
Thank you very much.
Bye-bye.
Thank you.
Have a great day. Bye.